There's another more exciting way to reconfigure systems and actuate these things, and that's to take advantage of that free degree of freedom that you have if there's a symmetry in the magnetic field. You only get a flux-pinning stiffness where there's a field gradient. So for a system like this, where the magnetic field is axially symmetric, the superconductor can rotate around the magnet with complete freedom. You can also make prismatic translational degrees of freedom. You can combine them. And this is the way to get at non-contacting kinematic joints. You can build a flux-pinned spacecraft system where the modules are bound together, and you can then define what degrees of freedom have stiffness and what don't, and the modules can form a kinematic mechanism where the components never touch one another. This is an interesting application, so we had to demonstrate it on the Airtable. Here are two sort of mock-up modules, and there's some issues in this video with friction, but the important points are that there's a superconductor here, there's a magnet here with an axially symmetric field, so it has an axial degree of freedom. So I can do this. I can push it around, and these two are pinned together by stiffness and the translation degrees of freedom, but it has this rotation degree of freedom. And then we've got this little faked-up reaction wheel here, and we can use that to sort of actuate the joint without components ever coming into physical contact with one another. Like so. There's always a couple of millimeters separation here, and again, we can engineer that separation distance and the stiffness depending on how we set up the interface. So, with this particular configuration, that 100-gram magnet, we get a flux-pinning range, not just the 100-gram magnet, but also the superconductor we looked at. We get a range of about up to 10 centimeters for these flux-pinning interfaces. And we can get a stiffness from 1 to 5 newtons per meter in this separation range that's with some distance between the modules. As they get closer, this increases exponentially. Damping is dependent on the superconductor properties, particularly the hysteresis in the superconductor. But interestingly, we can take advantage of other effects, like say eddy current damping in aluminum, to have damping that responds to the magnetic field. That, in fact, I ran an experiment similar to the one with iron behind the superconductor, where there's some aluminum plating there, and I managed to outrageously overdamp the system. So we can engineer the amount of damping that's present here without incurring losses from hysteresis, which make the system much more difficult to characterize. So we can design a system by placing materials with magnetic responses near the superconductors to adjust the flux distribution. We can introduce damping by placing conductive metals nearby the magnet. And we can probably change both those parameters and the range of a flux-pinning interface by carefully designing the distribution of our magnetic field, by choosing different arrangements of permanent magnets, different arrangements of superconductors. We've done a little bit of work there, but it's very preliminary. And we can manipulate these interfaces, these action distance interfaces, with either electromagnets that sort of push the interface equilibrium around, or by forming them with degrees of freedom, so that there's a kinematic joint. And I say that allows deterministic reconfiguration in the sense that you know you have stiffnesses in some degrees of freedom, and you know which degrees of freedom have zero stiffness, so you can have a system where you know where it's going to be freely moving and where you have some forces acting against that. One simplistic model is to say that the stiff degrees of freedom are constrained, but in reality there's some play to it, so hence the quotation marks there. Now, as a step towards designing these flux-pinned interfaces, we can take this frozen image model and calibrate it to experimental data, and we get this sort of design plot here, where I show the stiffness of a flux-pinned interface increasing towards the bottom right here on a log scale, against both the separation between the magnet and the superconductor, which would be a proxy for the intermodule separation in a modular system, and against a multiple of the dipole strength of the magnet, which is a proxy for the magnet mass, or if you want to use electromagnets, for the power that you're putting into them. And this is an exciting sort of result, because we have the current test data that I described here falls along this line. This plot is calibrated to that data, and they do match with the fits that I showed earlier. But we see that if we go for a stronger magnet, we can get a lot of interesting applications. You can get high stiffness but low separation, non-contacting grappling of space systems. You can get, say, a sparse aperture telescope, which may have modules spaced out more further away from each other, since the enhanced magnetic field gives you a larger range. And somewhere in the middle there, where you have a good combination of stiffness and range, you can assemble things, space stations, habitats, telescopes, what have you, in orbit. Now, that's not the most exciting thing about this. I think the most exciting thing is that our current test data also has things on, we have applications envisioned on the other side of it. With a smaller magnet, we can establish a CubeSat-sized swarm of satellites that are flux-pinned together with reasonable stiffness at a separation distance that's comparable to the size of the CubeSat. And maybe for very small magnets, we can even establish a swarm of flux-pinned spacecraft on chips that establish a very large structure in this non-contacting way. This is something that we hope to be doing in the next couple of years, to take some CubeSats and develop a flux-pinning interface to be demonstrated in orbit. And one of the interesting things about this interface that we envision is that we think we can take magnetic fields and arrange actuation such that this forms a non-contacting Stewart platform. And these two satellites are pinned together in a passive way, but if we do decide to actuate it, we can get sixed-off actuation between these two modules. So before I wrap up, I want to thank the other members of my research group, the Space Systems Design Studio at Cornell, and Tim's work as an undergraduate who helped us put together some of the demos and that mechanism demonstration that you saw, the Airtable demonstration. Laura Jones and Michael Norman are fellow graduate students working on other aspects of this project and helping out with some experimental things, and our advisor at Cornell, Dr. Mason Peck. And if you want to see some particular applications of flux pinning and some of the things it might be good for, there are a number of other papers being presented at this conference. So my little advertisement is that Michael Norman has presented a paper on using flux pinning for a sort of formation flight application to establish a network of satellites. Jessica Gersh looked at the specific application of forming a large aperture space telescope, and Laura Jones presented on using that space chip swarm that I alluded to earlier as a large-scale solar sail. So with that, I'm happy to take any questions you may have.